So we're going to pick up in this problem where we left off. And this would be a daunting problem if we didn't have a calculator, but since we have a calculator, it's really not so bad. All right, so when we get to this step, I have to remember that the plus 216i squared is 216 times negative 1, which makes this negative 216. And this minus 11,664i squared becomes a negative times a negative 1, so it becomes plus 11,664. So now I'm going to need to get my like terms together. I have a negative 45 and I have a negative 216, which gives me a negative 261 minus negative 108 plus 90 is negative 18i. So negative 45 and negative 216 give me the negative 261. Negative 108 and positive 90 give me negative 18i. Now, in the denominator, my like terms are 2025 and 11,664. So 2025 plus 11,664, and I get 13,689. These cancel, so this is just over the number 13,689. I'm going to separate this in case this can be reduced at all. Let's see. And I have negative 261 divided by 13,689. Math. Enter. Yes, that's negative 20 over 1,053 minus, let's see what 18 over 13,689 is. Math, enter, minus 2 over 1,521i. I went back and I was checking my work and I realized, I'm not sure because I can't error back up what my mistake was, but when the 261 divided by 13,689, when you hit math, enter, that's actually 29 over 1,521. I thought they had the same denominator when they reduced. I'm not sure. I must have typed something in wrong up here in the calculator because all the numbers are right here. This reducing. This is my final answer right there in complex form. All right. This now brings us to number 4. Number 4, we have what looks like is going to be a quadratic. I'm going to set it equal to 0. And then it will look like the quadratics we're used to seeing. Now, I could try factoring this, and I will find that it's unfactorable. I will try graphing this, and I will find that I can't see any zeros. If you can't factor, and you can't see it on the graph, you need to use the quadratic formula. The only way to find complex or imaginary solutions. Quadratic formula is x equals the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. And that's for a quadratic of the form ax squared plus bx plus c equals 0. So when I use the quadratic formula, this is a, b, and c, the first thing I do is I list my a is 3, my b is negative 5, and my c is 10. I have found if I do this, I tend to make less mistakes. X equals the opposite of b. B is negative 5, so it becomes positive 5, plus or minus the square root of b squared. So negative 5 squared. It is very important that you put that in parentheses. If you don't, you will end up with a negative 25 here rather than a positive 25. Negative 5 times negative 5 is positive 25. If you put it in your calculator like this, you will get negative 25 because it will square the 5 and then apply the negative. If you put it in like this, it gives you 25. This is what we are doing. We're squaring the entire b value. Minus 4 times a, which is 3, times c, which is 10, all over 2 times 3. All right, so I'm going to start using my calculator now. Oops, I didn't put that parenthesis there. And I'm going to do what's underneath the radical. Negative 5 squared minus 4 times 3 times 10, and I get negative 95 all over 6. See right away there's a negative under here, which is why I wasn't able to see my answer on the graph. So I'm going to keep going. I'm going to move up to here now, and I get that x equals 5 plus or minus. I'm going to pull that negative out and say I times the square root of 95 all over 6. And I check 95 and I see if it's divisible by any of my perfect squares. 95 divided by 4. Nope. 95 divided by 3 squared is 9. Nope. 95 divided by 16. No. 95 divided by 25. 95 divided by 36. It does not appear 95 is divisible by any of my perfect squares. So I can't simplify that. So I can leave my answer like that. If I need to write it as two separate answers, it would be 5 plus I square root of 95 all over 6, and 5 minus I square root of 95 all over 6. Another way to write it would be to separate it like I did here and have 5/6 plus or minus I square root of 95 all over 6. So I could write it like this, I could write it like this, or I can write it like that. They all mean the same thing. Let's do another one of these. Let's add 7, and I get x squared minus 2x plus 7 equals 0. I'm going to use quadratic formula. A equals 1, b equals negative 2, c equals 7. So x equals opposite of b, so it becomes positive 2, plus or minus the square root, b squared, negative 2 squared, minus 4 times a times c, all divided by 2 times a. Let's do my simplifying now. This is where I'm going to let the calculator help me. Got to be very careful. Negative 2 in parentheses squared minus 4 times 1 times 7. And I get negative 24 all over 2. I'm going to go ahead and I'm going to pull out that negative and say I times the square root of 24 all over 2. And I need to see if 24 has any perfect squares in it. I know 24 can be divisible by 4. So I already know that I could rewrite, I'm going to do this over here, the square root of 24 is the square root of 4 times 6. So that becomes 2 square root of 6. So I'm going to rewrite this as 2 plus or minus 2i square root of 6 all over 2. Now, you can simplify if all three of these can all be divided by something. It can't be that, oh, just these can, but not these. All three of these could be divided by 2. And I get 1 plus or minus 1i square root of 6 all over 1. So I could just write this as 1 plus or minus I square root of 6. So I did my simplifying of my square root of 24 over here on the side. This was kind of like my little side thought bubble here that I had to use in order to do that. All right, let's look at number 6. Number 6 asks us to prove that a squared plus b squared equals this. So I'm just going to leave the left side and I'm going to FOIL the right. A times a is a squared. A times negative bi is negative a bi. Bi times a is positive a bi. And positive bi times negative bi is negative b squared I squared. All right. The ABI's cancel, and I'm left with a squared. And remember, I squared is negative 1, so negative b squared times negative 1 becomes positive b squared, which gives me my theorem about complex conjugates. Complex conjugate multiplication theorem says that a plus bi times a minus bi is always going to equal a squared plus b squared. I'll give you an example. If you were to factor x squared plus 49, you could write it as x plus 7i times x minus 7i, because you would get first terms x squared, outer terms negative 7ix, inner terms positive 7ix. They'll cancel one another, and then negative 49i squared, which leaves us with, these cancel, negative 49 times negative 1 is positive 49. So we actually have a way to factor a sum of perfect squares if we're able to use imaginary numbers. Right? Let's go to number 7. We're asked to write this in a plus bi form. Negative 3 plus 7i divided by negative 10 plus 2i. I'm going to have to rationalize this, so I multiply it by its complex conjugate. Remember, the a stays the same, it's the b that changes. And I have to multiply it by the same thing in the numerator and denominator, so it's really just the number 1. Now I'm going to FOIL. On the top, negative 3 times negative 10 is positive 30. Negative 3 times negative 2i is positive 6i. 7i times negative 10, negative 70i. 7i times negative 2i is negative 14i squared. In the denominator, negative 10 times negative 10 is 100. Negative 10 times negative 2i is positive 20i. 2i times negative 10 is negative 20i. They cancel. And 2i times negative 2i is negative 4i squared. So this is going to become plus 14. This is going to become plus 4. 30 plus 14 is 44. Minus, because 6i minus 70i is negative 64i. Divided by 104, and now I will need to reduce each of these.